Okay. Oh, so many of us here live. I said to administrations there are at least 12 of us. But okay. Probably most of us will come later, but okay. So let's start. Dear Meatbags, hello. It's the third lecture of our mini course. Hope that everything works fine. Okay. So, what we did. So, let's start with a quick recap of what we did previous times. So, we introduced. First, we introduced axiomatic way, which is a productive way for working with hyperbolic geometry, but not very comfortable. So here, so we started with this axiom, which substitutes as a parallel postulate from Euclid. We proved the area formula for a triangle given its angles. So here A, B, and C are angles, and T is a maximal area of a triangle. Okay. So this might be proven from axioms, and actually there were some models which we will discuss more thoroughly today. So there were 5 models: half-plane model, disk circles model, disk lines model, hyperboloid model, and hemisphere model. Okay, so disk lines model is, or sphere lines model is Klein model, and this is defined as you can see in this picture. We have like parallel lines. We have that line. We define lines as some linear section of a pole, and and they are parallel if they are not intersecting. So some pictures about it. Okay, the second model is Poincaré model. It is a sphere circles model. So circles should be orthogonal to our boundary sphere. So this is those are some pictures and parallel lines in this model. Some pictures of this model. This was actually just an intuition, intuitive introduction. We defined several things, like the angles in this model are actually just the angles between circles. What does it mean? An angle between circles. Well, if you draw a tangent lines and you compute an angle, 2 tangent lines, and compute an angle between them, then this is an angle. Okay. So this is how motions in those 2 models look like. This is actually even a one-parametric family of motions. So there is also an upper half-plane model. which is constructed as half plane or half space model, which is defined as a set of points in one half space, and lines here are just circles orthogonal to boundary line, boundary plane, or boundary hyperplane, and this is or just vertical lines. Actually, I'm always forgetting to note that in Poincaré model, like this, so sphere circles model, there is actually one important. There is also one important type of straight lines that I'm forgetting to mention. Those are diameters of this circle or this sphere. And this is how we define this model. Actually, we are not defining so far any lengths between them, since actually first the formulas are difficult, and I will show you them today. I will show them to you today. Sorry for my English. And actually, the next model is definable in a way that allows to compute its lengths, angles, and everything you want. It's a hyperbolic model. So you take this subset of n+1 dimensional Euclidean space defined by this equation, and lines here are just sections of planes, just planar sections of this hyperboloid, and lengths here are just lengths of shortest curves along between 2 points, and angles are just angles between lines, in the sense that you again draw tangent lines between them, and this like that. So those and final fifth model is hemisphere model. Lines here are circles orthogonal to boundary. And this model is also conformal. Actually, the last 4 of these 5 are conformal. It means that we are easily computing angles if you by some visual sense. The first model, line model, is rather simple to get the idea, but here angles and lengths are not so trivial, actually. And okay, also these models are related somehow. I will remind you how somewhat later. Okay. So what was next? So I introduced some art. I introduced you this. Actually, okay. I forgot to write a slide about this. So actually, actually, I forgot to mention this in my slides for today. So this is about that if you take, for example, disk. So if you take a circle in this model, then its length is depending on radius of the circle nearly exponentially. Actually, it depends as hyperbolic sign, and I will tell you what is this, and the area of the circle is actually, how to say this, area of a disk, right? The inner of the circle. I forgot how this is said in English. What? Disk. Well, disk. Okay. So the area is also increasing exponentially, so there is lots of space here. So area is computed with angles. So no rectangles in this model. No, well, there are some artifacts like hypercycles. Those are equidistant curves in this model, which in Euclidean geometry are just lines, and here they are somewhat different. And in this in Poincaré model, it looks like a circle non-orthogonal to boundary. Okay. So, and there was the geometrical part. So everything I already defined. Yeah, so probably what else I need to say to you? Okay. So those how motions in three-dimensional hyperbolic space look like. Okay. So actually, we also talked about multidimensional geometry and ways to think about it. Let me not repeat what I just said. So there is an algebraic way, some geometrical ways to do this, some combinatorial ways to do this, some functorial ways to do this. So we will. So this was just like an intuitive part. So you can use it in your practice. And today we are going to discuss some technical moments. So next part is about inversion and stereographic projection. We defined stereographic projection previous lectures, so and I will remind you what it is. And let's first define what's an inversion in space. So consider an dimensional Euclidean space and a sphere in it. Define the following mapping, following transformation. Take point P and then send it to point P prime, which lies on the same ray as which lies on ray OP, and there is a relation length of OP multiplied by length of OP prime equals square of the sphere radius. Okay. What is this transformation? Well, this is called an inversion with respect to sphere. And what is interesting about it? Actually, it sends lines to lines or circles. Actually, it's first. Let me mention that it is if you take an inversion of an inversion, with the same sphere, then you just send P prime to just P. So P sends to P prime and then sends back to P. And what is also interesting about it, that it sends lines to lines of circles. So this line you see here is sent to this bold circle. Also, and to generalize this, linear subspaces are sent to linear subspaces or spheres. And the spheres are sent to linear subspaces or spheres. So circles are sent to circles or lines. So this punctured circle is sent to this punctured circle. And this punctured circle is sent to this punctured circle. And this bold circle is sent to this line. This depends only on the fact that will your line or circle pass through the center of your sphere. Yeah. So this is somewhat like a strange transformation of the space. And actually it is very useful. So even engineers use it in their practice. I forgot to actually add some inversion with it. Probably. Okay, probably. Okay. This is an engineering construction for what? For drawing a straight line with just mechanism. So you understand this probably. So this was a mechanical problem from 19th century to send somehow make a straight linear movement of a point. And actually, what do you have in BASIC? You just can rotate around some nail. So you just simply you just getting some circular motion, yeah, circular movements, and how to do straight line movements. This is doable by some interesting mechanism, which actually just construct an inversion of a point. And so yeah, actually, yeah, so you see black is sent to blue, and this mechanism just produces an inversion of a point. And if you just put your black point on a circle, then you draw a straight line. And then just add some detail. Let's wait for it. Yeah, here it is. So this is a circular motion, and here is an inversor. So this is a Lipkin-Poisselier inversor, or Lipkin-Poisselier straight liner. Lipkin-Poisselier mechanism. Well, there was a story about it, like Poisselier said that he invented this, and Lipkin then published his work about this, and then Poisselier said that this was his idea. So since then, this linkage is called Lipkin-Poisselier linkage. So this is how inversion is used. And So let's see closer on this inversion. So I said to use it, it sends lines to lines or circles, and circles to lines or circles. And actually, it also preserves angles. So it is conformal transformation. So actually, here you see a chessboard transformed by inversion. And my first question actually is why here you see some strange domain in the center. Can you guess? Where does it come from? I mean this. What? Yeah, this is an outer side of a chessboard. So this is what happened with border of our chessboard. So you see 4 circles, which are images of these 4 straight lines. Okay, and actually, okay, there is an exercise. Please maybe estimate radius of a circle of inversion here somehow. Actually, the previous question was a hint.
Yeah, you can see the radius of one of the circles inverted from lines.
Mm-hmm.
Actually,
Equal to what?
equals to the radius of one of those white circles.
Which white circle?
So we have 4 white circles in front of the 4 lines.
Equal to this. Actually, no. Okay. Some other guesses. Well, at least explain why. Maybe you are right, but I have a different answer. So definition was like this, yeah, and so you actually a hint here is to take some point for p as some point for p prime. What? To what? Yeah, 2 sides of a square cell. Yeah, right. Since actually we see that well, it's visually it's visual estimate actually, since we are comparing those 2 pictures, and we see that distance of so this distance is about square side, and then it is sent 4 times away. Yeah. So here, yeah. So the product is 4 squares of cell side. Yeah. And you take the square root and you get 2 sides of a cell. So what's happening in plane? Actually, we can think about our usual Euclidean plane as a complex, as a set of complex numbers. Then the formula here is like this for inversion. So W is an inversion of Z, and Z is an inversion of W. Actually, there is an exercise, computational exercise. Probably, actually, I will put this as your final homework. Yeah, I was said today that I need to do to make some final homework. We should finalize for that. Or maybe you want some hints about it. Actually, ask. Okay, so this is an invariant of any inversion. Okay. So how it is used? Actually, there is just some fine scheme, Mizuhashi-Volpert-Smith chart, which is used by electrical engineers for some tasks. And so here is here is a chart of impedances, of impedance matching. So we see here some. So you know what complex numbers are. So you see that here is somehow a circle corresponding to line real part of Z equals to 0. Yeah. Do you need to remind what is real part of complex number? No? Or yes? Tell me. And an exercise here is just to say what is actually which inversion is setting this picture to us. So how do we construct this picture from? So here is a borderline for real part of Z equals 0. So this is somewhat like this was like a vertical axis of our complex number plane. So this is actually another vertical line. Real part of Z equals 1. Here is imaginary part of Z equals to 0. And this is a line. Here is imaginary part of Z equals to 1. And yeah, so you see something like this. So I told you some properties of inversion. So where should be the center of inversion if we want to construct such a circle, such a disk? What? Middle of the second circle. Which is the second? Second largest. Real part of Z equals to 1. What is the middle? Center? So, okay. So here we are said that this is where we will. So this is actually this circle is passing through the center, right? So actually, since I see. But then this circle is will be just sent to itself, and this won't be a line. Any guesses? What in the middle of in the center of our boundary circle? And okay, but then this circle is not passing through it, and this should be somehow sent to a line. And I said to use it. Which?
The rightmost point.
The rightest point. Yeah. So this point is actually can be. So this is an intersection of all circles that will go two lines, and they are passed. So this is an appropriate center of inversion. So if you take this inversion, then you just construct a half plane of which half plane? This is when real part of z greater than 0. So okay. So is there any question for now? How this diagram works? Actually, no, since I'm not an electrical engineer, but you can read it in Wikipedia, or maybe you can watch some videos from YouTube. Well, yeah, actually, this is very interesting even for me. And yeah, Mizuhashi will pair Smith chart. Okay, so there is also a Möbius transformation. This is an idea for hyperbolic motion. So for complex number x, we have a set of Möbius transformations. F on x is just a fraction of two linear functions. So here their coefficients should be complex numbers. They are parameters of f. X is an argument. And theorem that this complex number transformation is just a combination of inversions and Euclidean motions. And what's next? For upper half plane, this defines a hyperbolic motion if and only if A, B, C, and D are real. So somehow to check that this preserves property of belonging to upper half plane would be, well, probably we have time for this. So yeah, let's solve this exercise. You can actually, by solving this, you can actually use the notion, this theorem. Since this theorem is very constructive, you just have to take. So it is very easy to construct these motions and inversions. Maybe you tell me some idea, and I will finish. Okay. Oh, how many people on Telegram? Telegram, are you good?
Yeah.
I don't hear really fast. Okay. So probably Ilfat is good, but maybe not good enough, and others are bad. Write me something if you hear me. I don't know. Just put pluses in chat. What? Okay. Hooray. So, okay. So A, B, C, and D are real numbers. And X belongs to upper half plane. Yeah. So Y such f on X is also belonging to upper half plane. Maybe. Okay, maybe you already want from me to do this for you. Actually, it's very well. You need some idea, actually. Maybe let me tell you then, if you don't mind. So, if you take x as a real number, so this is in a boundary of an upper half plane, yeah. If x is in a boundary, then imaginary part of x is 0, then x is real. And then f on x is real, right? So the border is sent to the border. And so we are just now need to check that that only the border is sent to the border, and only the boundary points. And if actually if you take a point in an upper half plane, then it is sent to a point in an upper half plane. How can we check this actually? So this transformation is continuous actually. Well, for x not equals to minus d over c, and this is just fine. This is almost continuous transformation. And then what? So if you are intersecting the boundary, unless you are intersecting the boundary, you won't be sent to another half plane. Yeah. Well, that's the idea. Okay. And then what? Then you just need to check that if you take some point from just one point from an upper half plane, then it will be sent to an upper half plane. So how to check this? Well, let's take x as an I, imaginary unit. So in the numerator we have AI plus b, in the denominator ci plus d, and so why it is actually having a positive imaginary part. Maybe here I need something even more. Let me check. Okay, let me check it. Upper half plane. Maybe I wasn't prepared for half plane motions. Sorry. Maybe I said to you something wrong. Probably I don't know. So shift delete. How to do this? How to know something? Okay, sorry. Maybe A, B, C, D are not just any real numbers. No, just any real numbers. Okay, so this is written here. And yes, oh, just forgot how to do this. Okay, let me do this as my next homework. Yeah. What? V6? Well, you can write it in chat or just show me.
Нужно просто выделить x. Вот, и получается инверсия плюс просто движение по вот этой штуке умножения. Ну да, это остается легко.
Okay. So yeah, this was just. So you are just taking A over C, and here what is rest is somewhat a number over Cx plus D. Yeah. So A divided by C is just a real number. It's adding doesn't or negating doesn't take you out of an upper half plane. So and the other part is just an inversion. So number over Cx plus D. So it is just like an inversion plus maybe shift plus maybe what? Maybe homosthetical relation. What is homosthetical? It's how to say this? Multiplying by C. Yeah. And this won't be taking you out of your upper half planes. So yeah. Okay. Maybe a tough problem for a beginner, but it's some technique. So stratigraphic projection, what it is, and this is what we defined last time. So you take a north pole of a sphere and then just project your sphere without this north pole by central projection to a plane which is some horizontal plane according to a vertical line from center to north pole. Yes. So last time we saw that this transformation just sending circles to lines and circles in hyperplane. So this can be defined in many dimensions too, and this property also works. So here is another picture. So actually this is setting correspondence between hemisphere and sphere circles models, and also between half space and hemisphere models, like you see in these pictures. Yeah. So here is here. So if a circle on a sphere is passing through a north pole, then it is sent to okay, some mistake in English, to lines on hyperplane. Yeah. So you see here how to what should be a pre-image of chessboard. This looks like this, and also stratigraphic projection is an inversion. So this is an inversion between this sphere and this hyperplane. Okay. So questions so far? Ask something. Yeah. What?
When the result only if this determinant is bigger than
if it is positive.
That's what I want to ask.
Yeah. This was, yeah, okay. If determinant is positive, so I I already forgot this actually. Yeah. So here this determinant should be not just zero but even positive. Okay. Then it is algebraically obvious. Thank you. Another question. Okay, then probably move on. So let's move to motions. So we see. Okay. I forgot to start some slides, but probably I will explain what I mean. So this is just, well, there is a link on the full article about this is planar motions in a disk circles model. So here you see those diameters that I talked about in the beginning. Yeah. So those are somewhat shifts, some shifts, and this is a ternary tree. Yeah. Okay. Motion types. Why did it put this? Okay. So okay. So this is what I'm going to explain in another way. So n-dimensional motions. Actually, I told you that it is much easier to define anything on hyperbolic model and then somehow to project to other models. So if you want to define something, you just start from hyperbolic model and then just send your formulas to n dimensions. So okay. I said to you that motions of hyperbolic geometry are just linear transformations preserving this quadratic function. Linear transformations in n+1 coordinates. And from linear algebra courses, we know that this is equivalent to this matrix relation. Set of such matrices is denoted by so as O n1. This is a pseudo-orthogonal group, so pseudo-orthogonal transformations, since most coordinates are just, well, this is mostly looking as our usual distance formula from 0 to the point x. And this is nearly orthogonal matrices, but they are somewhat different. Well, I didn't find any I didn't find and remembered any explicit formula for this, but here is a hint from Lie group theory. Lie group, what is Lie group actually? Let me show you. So there was a mathematician from Norway, Sophus Lie, who defined Lie groups. Okay, maybe. Oh, right. Sorry. Okay, Sophus Lie. So this guy. So he defined his Lie groups, and what is it? It is some continuous sets of matrices, those sets should be closed up to operations of matrix multiplication and taken an inversion. So here is a theorem from this Lie group theory. So you take so if you want to find all such matrices C, then you just take matrix exponential of matrix A, or some modified version, I1n multiplied exponent of A, where A satisfies this relation, and I1n is just this matrix with minus 1, ones, and zeros. So this is a so-called Lie algebra, the set of such matrices A. This is a tangent Lie algebra for this Lie group of O and 1. And so here is a linear relation of for matrix A. Actually, you can find defining relations for elements of this matrix. Okay, and don't know, probably will we do this? Not sure. Actually, it's very easy. So you just well, maybe this will be your home task. Okay. And some generators for motions. So actually, maybe this is even a better exercise. So those transformations, this group is also called a Lorentz group. Usually Lorentz group is for n equals to 3, since when n equals to 3, then it has an application for relativistic physics, and so here we have Lorentz boost defined in this way, and Lorentz rotation defined in this way. So here V is a vector of length lesser than 1, gamma is a function of this vector, and then you take this something that is called Lorentz boost. It is transformation. This matrix is preserving this this quadratic form. Lorentz rotations are also, and the third generator is some mirror symmetry with respect to hyperplane. So it is sending one of the coordinates to, like you may take some sending one of the coordinates to opposite or just other mirror symmetries. But this list is actually complete for generators of these motions, and so yeah, they are generating this. Not sure that we have time for this, but okay. Let us make a short break for now, for 5 minutes. Yeah, and after the break, I will discuss another motions that are generating this set of motions. So we will know lots of things, and yeah, okay. So 5 minutes break. Probably you can solve this exercise during the break. Oh, why video stopped? Why video stopped? Okay. Please actually write me in chat if our video is stopping. I don't look in video chat and actually don't know if this is happening. Actually, I saw in video recordings that this happens sometimes, but not for long. Okay, good. That you saw the preso. But I need to know when you just don't see anything. Oh, sorry. Okay, yeah. We'll just send you links. Chile. Yes, this is the whole presentation, which is starting. And yeah, so this is the geometrical part. So this is what I already sent to you. Something that for applications. Okay. Okay. So, so let's share this. Why do you asking for? So you don't access presentations if I am just sending you a link. Okay. Okay. Wait, Alexei. Wait. Ну да, будет список задач. Ага. Okay, dear Meatbags. Let's continue. Let's continue. So, probably this is a good exercise for homework. Okay. Several other notions. So, n-dimensional motions are generated by just hyperplane symmetries. You need at most n+1 hyperplane symmetries. Every motion is defined by movements of n+1 points in n dimensions. This is just like in Euclidean space. This can be proven the same way as in Euclidean geometry. Actually, this is sometimes it is called as an lemma of n+1 nails, or in planar case it is lemma of 3 nails. Actually, I'm not sure. Lemma of 3 nails. Let me check. Okay, 3 nails were used to crucify Jesus Christ. Okay, this is not what I was looking for. Okay, maybe later. So, and every motion is defined by motion of ideal points. So, okay, here is a good exercise for matrix C of hyperbolic motion. Compute the corresponding motion in Klein n-dimensional ball, which is about sphere lines. So I'm reminding you that they are related in a way that you take a central projection between hyperboloid, this upper part of it, and a plane x0, which is defined as x0 equals 1. So let us do this now. How to compute such a motion when you know matrix C of hyperbolic motion. In coordinates, of course. Okay, let's switch screens. So you have okay. So you have this hyperboloid. This expression, oh sorry, minus x0 squared equals to -1, and this is what is drawn here. Yeah. So here you have the 0 point. And this is the hyperplane x0 equals 1. So matrix C is like Cij for I and j is from 0 to n. And your x 0 xn for point on hyperboloid is just sent to where? No, not there. C0i xi for zeros coordinates, sum over I. So here is C1i xi. This is just reminding. I'm not solving it. Cni xi, right? Sum over I. This is what matrix C does. And what is it doing when you are central projecting on this hyperplane? First, probably a hint how to compute this central projection. So let P be this central projection. How to project it from the 0 and to a point on hyperplane x0 equals 1. So what will be the zero's coordinate first? Yeah, 1, just 1. Okay. And yeah, so how to compute other coordinates? So actually, what can we use? So those 3 points are lying on the same line, yeah, and so they are just on the same one-dimensional subspace. So those two vectors, this vector and this vector, should be linearly dependent. So construct a vector which with zero's coordinate 1, which is linearly dependent to this vector x. Yeah, just divide x1 over x0, x2 over x0, and the last one is xn over x0. So, okay. So this is just a projection. So how does our projected version of motion looks like? Well, zero's coordinate is not very interesting since it's always 1. And actually, what we have here. So x0 was sent to something like this, yeah. So probably we should change our denominator everywhere to this expression, right? So this c tilde is just sending our point x1 over x0, x2 over x0, etc., xn over x0 to what? Actually, just is everything visible on the screen? Okay. So how coordinates change? Yeah, this is in the denominator. Yeah. So here we have c1i, xy, etc. cni, xi over c0i, xi. Well, yeah, looks like, but this is not enough actually. Since actually we don't have any thing like x1, x0, x2, xn on this plane, yeah? There will be another coordinates, yeah? So the coordinates here are just these numbers. We don't know what is x0 here. We can find x0 by this relation, actually, yeah. So since we will just solve this equation here. But actually, that's not enough, since we need to express this as a function of x1 over x0, x2 over x0, xn over x0, and this will give us the answer. So probably how to do this. Actually, this trick from projection geometry. Let's just divide everything in numerator and denominator by x0, right? Yeah. So here also x0, xy divided by x0. So this is just equal, right? Tell me something if you agree or not. Are you agree with me or not? Okay. Some people agree. If someone don't understand, then just ask something. Okay. And yeah, so actually I can rewrite this as well. I have not much place, so we may put this as y1, y2, yn, and this will be just expressions. Those just will be expressions of y's, not just an expression of x. So and this will define our motion on motion inclined model. Yeah. Okay. So was this clear enough? Yeah. So several tricks actually. Okay. So this might be a home task, actually, another home task. So the same is for Poincare model. This is for sphere. So this is doable by the notion that they are related as this central projection from the point -1, 0, 0, 0, and here is the hyperplane x0 equals 0. Yeah. Okay. So this is how motions are computed. Actually, okay, wait, sorry. I understand now that Telegram didn't see this. Actually, yeah, let me firstly note that. Okay, so those are called linear, fractional linear transformations, since we have just fractions of linear functions, yeah? In numerator and denominator, there are linear functions on y's. And this is somewhat comfortable. Okay. Let me change the screen. So this was what I taught about n-dimensional motions. So here you can see hyperplane x0 equals 0. This is a Poincare model. And here you can see a point -1, 0, 0, 0, which lies on hyperbolic, but on the lower sheet of it. And this is so this doesn't so this is not included in our hyperbolic model, just some point in space, yeah. And you just take this central projection. Actually, answer is very similar to the answer of previous problem, but somewhat different. Okay. So there is a theorem. I didn't mention this as a theorem in this slide, but okay. Motions in Poincare blow, hemisphere, and upper half space models, they are just compositions of inversions and Euclidean motions. Yeah, and so that's what I told you about inversions. And for a Klein model, we saw, when we solved this exercise, we saw that those are linear fractional transformations. Okay, so let's move to 3D motions. Okay, how can we model this actually? Actually, there is a very nice relation with some other part of the science. Let's define quaternions. This history of quaternions were that people were admired by idea that we can multiply. Probably we can multiply three-dimensional vectors as we do with complex numbers on the plane, yeah. But they didn't find any formula, and then Lord Hamilton from Edinburgh were working very drunk on the bridge, and then suddenly invented the rule for multiplying four-dimensional vectors. He wrote it on the bridge over the river, and so how to multiply vectors A, B, C, D, and A1, B1, A prime, B prime, C prime, D prime. So consider them as an expression of A plus BI plus CJ plus DK. And we think that A is multiplied by 1 here, and how to multiply this. So so everything multiplied by 1 is just the same thing, yeah? I multiplied by 1 is I, j multiplied by j is j, k multiplied by k is k. When you take squares, so you get minus 1s for I, j, and k. Here you see. For 1, this is again 1. The square of 1 is 1. The multiplication of I and j is computed this way. I multiplied by j is negative of j multiplied by I, and it is k. So this multiplication is not commutative. This is like matrices. And gk equals minus kj equals I, ki equals negative ik equals j. So probably my audience here knows how to multiply quaternions. So if you want, we can do this. If anyone wants, we can do this. If you're not familiar with this, is just very actually this is very important stuff for computer graphics and for spacecraft motions, and this is the most well, one of the most comfortable techniques to do this. I will briefly mention what I mean. So, no need for multiplications of quaternions. Okay. Lots of people know already. Okay, we're all educated people. So, okay, then we can express these quaternions as such matrices. With complex entries. The multiplication of such matrices corresponds to multiplication of such expressions. And taking invert element for quaternions quaternion is just computable by this, so it is easy for you, I guess, to check that that q powered by minus 1 multiplied by q equals to 1 then, for q not equal to 0. So when all a, b, c, and d are not equals to 0, then we have it is an invertible element in this algebra, and we know that, and probably then, as you are an educated people, but I will just repeat it for you, that quaternions are very comfortable for expressing Euclidean 3D rotations. So you just take this quaternion u of unit length, Euclidean unit length. Then actually you just check that square of it equals to minus 1, and then you can consider this as a complex number. And yeah, so then you just take it as a Actually, okay. Yeah. This formula is correct. Okay. Then actually you can take quaternion, another quaternion Q for angle theta as this, and this is somewhat like a complex number, but actually, so well, for different use, you just get another set of complex numbers. They are all different, but they are just so by real part, which is multiples of ones, and imaginary part, which are multiples of u. And you just take this expression L. So transformation L just send P prime to point P prime or point P to Q P Q power minus 1 conjugation. And this is actually rotation about an axis of generated by this vector, and this is rotating by an angle theta or theta or half of a theta. I don't remember actually. Probably by theta, right? Does anyone remember right now? No? Okay. Okay. So, and this is rotation in 3D space, since we can take P as another just imaginary quaternion. So imaginary means it no coordinate of one for one. Okay. Actually, so this was not written here, but yeah, here is this reason: rotation of angles theta. Okay. Let us not check this in, if you know but don't remember. Okay, so this video of quaternions as three-dimensional rotations. Probably, since you say that you all know this, then we won't watch it. Tell me something if you want. Okay, this is a short video, actually. Okay.
You know, and I want you to do this other website, goes to the short sequence of what we're calling explorable videos. It was done in collaboration with Ben here, who some of you may know is that guy who wrote the
Oh, sorry.
You know, and I want you to do this other website, goes to the short sequence of what we're calling
Yeah. Sorry.
It was done in collaboration with Ben here, who some of you may know is that guy who wrote the computer engineering channel. And if you don't know the video, viewers of this channel will certainly enjoy the content of this. So do check that. This collaboration was something a little different for both of us. And all of the web development that made these explorable videos possible is completely independent. I don't want to say too much about it here. It's really something you have to experience for yourself. Certainly, one of the coolest projects that I've had the pleasure of working on. Before that, though, I want to use this video as a chance to peek inside a little bit of surrounding context. So, to set the stage, last video I described alternatives, a certain four-dimensional number system that the 19th century versions of Holmgren and the old man and well called easily for how commonly we conceive it. And perhaps you too are wondering why on earth did anyone bother with such a big ABCD number system? Well, one of the big reasons, especially for programmers, is that it gives a really nice way for describing the UV orientation, which is not susceptible to bugs and edge cases of methods. I mean, they're interesting mathematically for a lot of reasons, but this application for computer graphics, like robotics, we have in involved video information is probably the biggest use case for quaternions. To take one example, a friend of mine who used the word hacker and the chat. Delighted to tell you about shipping code to hundreds of millions of devices that uses quaternions to track its own model for how it's floating through space. That's right, your phone almost certainly has software doing somewhere inside of it that relies on quaternions. The thing is, there are other ways to think about computing rotations, many of which are way simpler to think about than quaternions. For example, we get familiar with linear algebra, we'll know that 2 by 2 matrices can really nicely describe 3D transformations. And a common thing that many programmers think about constructing a rotation matrix for this kind of rotation is to imagine rotating an object around 3 easy to think about axes, where the relevant angles for these rotations are commonly called Euler angles. And this mostly works, but one big problem is that it's vulnerable to something called pinball, where the 2 of your axes of rotation get lined up, you lose a degree of freedom. And it can also cause different.
Actually, this mechanism was in spacecraft before quaternionic computers, and this almost led to some catastrophes. For Apollo 11, this ended safely actually, and after the spacecraft flight in sky somehow like this, astronauts just joked, please give me some force ring. Okay.
Difficulties and ambiguities when trying to interpolate between 2 separate orientations. If it cares for more details, there are many resources online for learning about Hyperbolic, Hyperbolic, and I've left links in the description for the field. Not only do quaternions avoid issues like Hyperbolic, the equally seamless way to interpolate between 2 three-dimensional orientations, one which lacks the ambiguities of Euler angles, and which avoids the issues of numerical precision and normalization that arise in trying to interpolate between 2 rotation matrices. To warm up to the idea that multiplication in some higher dimensional number system might be used to compute rotations, take a moment to remember how it is that complex numbers give us a good method for computing 2D rotations. Specifically, let's say you have some point in 2-dimensional space, like 4, and you want to know the new coordinates you get if you rotate this point 30 degrees around the other. Complex numbers is sort of a snazzy way to do this. You take the complex number that's 30 degrees off the horizontal with magnitude 1, cosine 30 degrees plus sine 30 degrees times I, and then you just multiply this by a point represented as a complex number. The only rule you need to know to carry out this computation is that I squared equals -1. Then, in what might feel like a bit of black magic for those first learning it, carrying out this product from that one simple rule gives the coordinates value of the point. Point rotated 30 degrees from the original. Using quaternions to describe 3D rotations is simple, though the look here is slightly different. Let's say we want to rotate some angle about some axis. We first define that axis with a unit vector, which we'll write as having I, J, and K components, normalized so that the sum of the squares of those components is 1. Similar to the case of complex numbers, we use the angle to construct a quaternion by taking cosine of that angle as the real part, plus sine of that angle times an imaginary part. Except this time, the imaginary part has 3 components, the coordinates of our axis of rotation. Well, actually, we take half of the angle, which might feel totally arbitrary, but hopefully that's going to make some sense by doing this whole experience. Now let's say we have some cube, which we'll write with I, J, K components. And you want to know the coordinates that you get when you rotate this point by your specified angle around your specified axis. What you do is not just a single quaternion product, but a sort of quaternion sandwich, where you multiply by q from the left and the inverse of q from the right. If you know the rules for how I, J, and K multiply amongst themselves, you can carry out these 2 products by expanding everything out, or realistically by having a computer do it for you. And in what might feel like a bit of black magic, this big computation will return for you the rotated version of the point. Our goal is to break the step and visualize what's happening with each of these 2 products. I'll review the method for thinking about quaternion multiplication described last video, and explain why half the input is used, And while we will classically right, but we didn't this. On the screen now, and at the top of the search, you'll find a link to user.net/quadratic patterns, which is where the historical data where I explain what's going on with this location computation. It's just really, either did something awesome. So at my rate, it's just a couple minutes to go look at it. But I don't want to get into the full experience.
Okay. So I managed to continue today my career as a React streamer. So I'm on the way of my first trillion of subscribers. Yeah. Actually, I wanted to say that there are several different models for computing rotations. For example, author of Megakure game we saw last time invented his own system, even for many-dimensional rotations, which somewhat differs from quaternions. And he also states that it is more optimized. I'm not sure actually about it, but at least this works in many dimensions. Yeah, some interesting notions. Oh, yeah, like faster, like lesser multiplications, probably. I don't know actually. I didn't check, sorry. Okay. Some interesting fact. And, well, what was this about? What for this was? Actually, how to define three-dimensional motions for, motions of 3D, okay, sorry. So, define our upper half space as such a set of quaternions. So Z here is a complex number, A plus BI, and T is a positive number, real, yeah. So no K part here. And then let's take this matrix, complex matrix, with entries in 1 and I, complex number generated by I. Yeah. So, and then define motion this way. So we take Q from this H3 and then just compute this expression, which is actually equal to this expression. Okay. And these transformations preserve. Actually, I forgot. Okay, this will be. This is what I will say later. This transformation preserves hyperbolic distance, which is logarithm of this expression for A and B points and C, D ideal points of line in AB. Well, this is at least definable. Later, I will show you some pictures for this formula. So, yeah, so this is a formula for three-dimensional motion. Actually, so that's how you can work with, I don't know, relativistic physics, for example. Yeah. Sometimes. Okay. So. And yeah, so usually in relativistic physics, you have that your velocity is below speed of light, and then they live in a ball of radius c, and this just give you hyperbolic geometry of velocities in relativistic physics. We will mention this tomorrow. Okay. Okay. much time do we have and how much is okay, about, so we're about in the middle. Yeah, so this will be short. So let's go to hyperbolic trigonometry. What's this? So those are some formulas. Let's define hyperbolic sine as difference of exponent of x and exponent of minus x, always divided by half. Hyperbolic cosine as half sum of these two exponents. Hyperbolic tangents as a relation of hyperbolic sine and hyperbolic cosine. So this is hyperbolic coseconds, hyperbolic seconds, hyperbolic cotangents. In Russia, we usually call this as not as, so we call sinus sine as sinus. So hyperbolic sinus is sinus, cosine is other. Well, we call cosine as cosinus. So hyperbolic cosine is either cosinus or cosinus. And I like to say that we have usual cotangents and cotangents. Yes, this is a joke in Russian. Okay, let's move on then. So those are several relations between those functions. So here is property that property for adding angles. Well, not really angles actually. This will be a hyperbolic angle. I will mention you later what it is. So what for are they used? Actually, since exponents are multiplied in a way that we take, so those two exponents are multiplied as 1. So this might look like points on hyperbolas, and actually also for rotated hyperbola we have x squared minus y squared equals 1, and this is just looking like this relation between hyperbolic cosine and hyperbolic sine. So this makes it look like analog of a circle. But for now, actually, but for us, actually, hyperbolas are just somewhat like lines in hyperbolic geometry. So this is not not very correct, but there is also a relation actually with angles. Okay, so here are plots for those hyperbolic trigonometric functions. So hyperbolic tangents is usually used in machine learning, since we have it almost -1 for almost half of the point, and almost 1 for almost half of the points. And this is the perfect activation function. For machine learners, except for that this is this takes too long to compute it sometimes. Okay, so this is the physical meaning of hyperbolic cosine. Its plot actually is a catenary line or chain line, as we call it in Russia. So here you see some bridge, and here you see chain. And usually people think that this line is hyperbola, but it's not. It is, or not probably circle. but it is not. It is part of the plot for hyperbolic cosine. And also, hyperbolic cosine has several other physical meanings, but let's skip them. You can read them in corresponding books or on Wikipedia. And okay, about hyperbolic trigonometry. So let us define hyperbolic angle as this. So take 2 points A and B on your hyperbola and your origin of coordinates, 0 point, and take this curved triangle. So OAB. So here is this side is not straight line. This is part of your curve of your hyperbola, and then hyperbolic angle is defined as an area of such set. Okay. Actually, what is interesting about this area is that it is preserved by any hyperbolic motion for this hyperbolic line. So what is this hyperbolic motion? Actually, this is just, as I told you, that it is a linear motion preserving form of some quadratic form, and we have here just rotated hyperbola. So here our quadratic form looks like xy equals to 1. Yeah. So if you just transform your point A to a point S A x and A y divided by S, and your point B correspondingly, so multiply the first coordinate by S and divide the second coordinate by S, then this angle is then this area is preserved by this transformation. Well, actually, let me shortly mention why this holds. Okay, so actually this is some computation. Which can be checked by the notion that if you take this curved trapezoid from A to B, yeah, between these planchet lines, then the area between those lines is just natural logarithm of B divided by A. And as you can see, so B divided by A is invariant under multiplication of S. Yeah? So this will be actually sorry, A and B are just coordinates, x coordinates for these points, and I told you something somewhat about the coordinates on axis y, but this is just 0. So I meant these points. Yeah. So this area is preserved by this transformation, by hyperbolic motion, and to make it looking more or less more invariant, in coordinate free, more coordinate free. Let us define this as a hyperbolic angle. So actually, this hyperbolic angle is not what it is not bounded by any number, since an area below this hyperbola is just infinity, and you can take A and B just very far away from each other. So it is can tend to infinity. and then hyperbolic angle is not bounded. Okay. Then actually hyperbolic angles are the function for standard hyperbola. Hyperbola x squared minus y squared equals 1. Let us take this curved triangle and denote its area as A. So then, which triangle actually? We take we take symmetric points. Those 2 points are symmetric, and then form this triangle with the origin of coordinates and those 2 symmetric points. And then, if this area equals to A, then these 2 points, then this upper point is hyperbolic cosine of A. Then its x coordinate is hyperbolic cosine of A, and y coordinate is hyperbolic sine of A. Yeah. And for other point, you just take plus hyperbolic cosine of A as x coordinate, and minus hyperbolic sine of A as this coordinate. Well, and actually there is another picture. Just mentions that if you are not taking this symmetric triangles, then you just put it as then you just have half of the area, A divided by 2. Okay. So some hyperbolic trigonometry is arc functions. So here you see hyperbolic arcsine, hyperbolic arccosine, hyperbolic arctangents, and so on. They are definable by these formulas. So here are the reports. They are looking more or less like usual logarithm, but maybe shifted away. And here are, here are differential equations for these functions. Actually, very similar to what we have for usual trigonometry, like derivative of hyperbolic sine is hyperbolic cosine, derivative of hyperbolic cosine is hyperbolic sine, and second derivatives are just the same functions for hyperbolic sine and hyperbolic cosine. For hyperbolic tangents, we have this beautiful differential equation, and this is actually used in machine learning, since when we, probably if you are machine learning, you know how to do, how can this be used, since we have to compute gradient after we computed our activation functions, and this is the way to do this expression of gradient as a function of your activation functions, as a result of activation functions. Okay, and yeah, so after the break, so actually, any questions for now? We actually, please ask me something during the after the break. We are going to define lengths, angles, well, angles are mostly already defined, and areas for hyperbolic geometry. Actually, this will be the last part for today, and this will be, well, actually, we will define a lot, and we then used it somehow. Okay. So 5 minutes break. We will start at 1806. And let me check those who are attending online. So, Piotr Kushnir. Daniel. Ксения. Карина. Александр Кузьмин. Эй. Вася Рагусов.
Hello? Hello?
Probably Messumachi. Not sure. If I'm correct, tell me. If I'm not correct, then also tell me. Here and home.
Hello?
Oh, actually, I don't hear you actually. Strange. Oh, just write in chat if I'm not correct. Your name.
For my name?
No, I still don't hear you. Okay. Okay. So, Messumachi. Okay, but Karina, okay, but you're a scientist. Okay, Fatma, but you're just signing this, Karina. Okay, this is like a Russian name. Okay, dear Meatbags, let's continue. So, how to compute something in this geometry? We already saw some formulas for motions. We defined hyperbolic trigonometry, and actually, we will use two ways for expressing lengths, especially lengths for this geometry. One way is elementary, it means for high school level, and the second is differential geometric for university level. Okay. So let me start from differential geometric way, just to scare you. So
Could you finally present the visual describe to the high school?
so this is high school for you.
No, I mean, could you finally present this one to the high school?
Okay. Yeah. So every high schooler should know this. And okay. So what is metric tensor? So if you have some surface or subvariety or submanifold, then you just define lengths for a curve between 2 points as like its length on the surface, yeah. And how to do this? We can define this as some integral, and here, so we define this expression for local distances, yeah. So so if you take ds squared is the sum of is a quadratic function of dxi's with coefficients as functions of x. Yeah. So this is what a square of distance between close points look like. Approximately, this is just some differentiation of this distance, derivative of this distance for directions for small vectors x1, dx2, etc. dsn, with coordinates dx1, dx2, whatever, etc. dsn. So instead of dxi, you just substitute its derivative over time t, and then you just compute this as a local length, then take as a square of local length, then just take the square root of it, and then just integrate it over time. So this is how lengths are computed in this in general way for differential geometric way. Yeah. So relation between metric tensor and angles. So we saw a relation between lengths and metric tensor, and for angle we just I told you that we just take an angle between velocity vectors, and then what? So the length of velocity vector is computed as square root of metric tensor substituted in which is velocity substituted, right? Yeah, and then we have a cosine theorem that well, we can consider this metric tensor as a scalar product, and then just compute cosine of theta as a relation of scalar product to the product of lengths. Yeah. Usually, actually, those j's are chosen to be such that d square is positive. Well, some mathematicians explore possibilities where it can be negative, but it's not for us today. So, yeah, and areas, volumes, multidimensional volumes are then computed as integrals expressed metric tensor coefficients. Well, I'm not sure that this is very interesting for you. Then, well, if you want to know something like what I was talking about for recent 5 minutes, then please take a course on differential geometry. I'm just defining everything here. Okay. So, metric tensor for Poincare-Beau model and Rupert half space model. So take for Poincare-Beau model, you just take sum of dxi squares and divide it by square of 1 minus square of the norm of x for a point x. This is non-zero since we are inside of a ball. Yeah. And if we take this and for, so yeah, this is a metric. You can integrate it to compute length of a curve. Okay. And then the metric of the upper half plane model. Actually, didn't have enough time to put the complete formula for n dimensions here, but you can guess. So you take x1, x2, and etc. xn with xn greater than 0, yeah, and then just take sum of dxi squared and divide it by xn squared. Yes, and well, this is symmetric. You can compute length for now. Actually, there is an exercise to check that if we take usual, maybe okay, not very much left for this lecture, and 45 minutes actually. So let's compute metric for hyperbolic model at point x0, x1, etc. xn. So use some projection correspondence. So actually, yeah. Let's take this and somehow I see. Yeah, so let's switch the screen. What? Hello, Alexei. let's compute. Yeah. So does Telegram see what I'm doing in Paint? Write something in chat. Yes, it seems that I don't hear you today. Okay. So you see something. Okay. So let's compute metric for hyperbolic model at point X. I see. Wait. Okay. So we need, no, so this was a Klein model, yeah? Okay. Okay, then let me return. So let me then copy. Yeah. Let me then copy correspondence for more between models for, yeah, here. No, not sure. Okay. So equation for hyperbolic is written. So this is x0 equals 0. This is point minus, sorry, minus 1, 0, 0, 0, 0. And you take a central projection from this point to this plane. And yeah, sorry, again, I just erased okay. So this is enough information for an exercise. So do you need a hint to what to do actually? Let me briefly mention what you need to do. So you just you need somehow to express these differentials in metric tensor. So how to do this? Those are basically derivatives, yeah? So just express this as, so compute how derivatives correspond to each other. Yeah. Like you, like by coordinate by coordinate. How do they correspond to each other? And probably the hardest part for this is to compute the central projection formula. But I already told you how to do this for another, for different case when you central projection with the center of origin of coordinates, and this is just a modification actually. So let's do this. Посчитал. Ну да, ну сейчас, ладно, я сейчас. Просто тогда мне придется. Да, я кину так. Ладно, просто мне придется переключать экран, когда тут просто не будет видно. Да. Ну да. Ну, скорее из Poincaré гиперболоид, ну да. Ну, короче, метрику на вот этой поверхности получить. Да, на гиперболоиде.
А, как? Снять ее с...
Да, шара. Actually, the answer will be very easy, and I nearly told you even today the answer here, so here is the ring for current hesitation. Теоретически они все открываются. Ну там, в общем, первые несколько все должны открываться. Угу. So probably you need a hint. For example, how to compute the projection. No? Oh, yes. Oh, yes. Okay. So here you have, for example, so here you have point x0, x1, etc., xn, right? And it satisfies this relation. Here you have this point -1, and you want to, well, for example, you want, if you are given this data, you want to compute the point on this plane x0 equals 0. And, well, if you are given these 2 points, then you want to compute the third point. So let us start with computing this point from these two. So how to do this? So these 3 points are lying on the same line, and what you need to do is to use this in a way that, you form a vector from this point to this. So this is vector x0 minus 1, x1, x2, etc., xn, right? Okay, it is visible on the screen. And yeah, so here is -1, remember. Okay, so, you have a point, so you have a point 0, y1, y2, etc., yn, on this plane, yeah, x0 equals 0. So you just do what? This point is those are just coordinates for point. And what is the vector? The vector is this point. Let us call this point A. Yeah, and this point is P of x. So vector A from A to P of x is -1, y1, y2, etc., yn. And you know that this vector and this vector are collinear. So you need to just compute y1, y2, etc., yn from x0, x1, x2, xn, such that it will be collinear with this vector. Yeah, so this is some very huge hint for this computation. Actually, the rest is, for projection at least, is what we already did. Maybe make you guess what I need to do here. So I need to compute y1, y2, yn. So what? And those two vectors are collinear, this one and this one. And the first coordinate for the second vector is -1. And the first coordinate for the first vector is x0 -1. So what to do? Oh, proportion, yeah. Actually, someone said something and I almost hear this, but not sure. Probably Telegram should write something in chat if they want to answer. Please for today. Not sure how it works. Okay. So -1. The next is so they're linearly dependent, yeah. So they are proportional to each other. So they're differing by multiplication by some number. Yeah. So you just divide. Yeah. x1 divided by x0 minus 1. x2 divided by x0 minus 1, etc. xn divided by x0 minus 1. Yeah. Okay. So probably we need also some other things like or maybe this is enough already. Well, you can compute, for example, relation in the other way. Well, how to express x's from y, but at least you know that you have this relation. Is it very helpful? Yeah, it's very helpful actually. So you have like x1 squared plus etc. plus xn squared equals to x0 squared minus 1, yeah? And probably you know some formula. So this is x0 minus 1 multiplied x0 plus 1. So x0 minus 1 is just x1 squared plus etc. plus xn squared divided by x0 plus 1. So also we have that yi equals to what? 2xi multiplied by x1 squared etc. plus xn squared and divided. Oh, no, sorry. Mistake. Multiplied by x0 plus 1 divided by x1 squared plus etc. plus xn squared. Okay. So, yeah. So it is easy for now to compute the norm of y. Actually, since we have norm of x, and this is actually, well, this is norm of y actually for in our notation, yeah. Do you follow me? It's that we need norm of y. squared. So, okay, let's compute it somehow. Actually, okay, this is x1 squared divided by x0 minus 1 squared plus etc. plus x1 squared divided by x0 minus 1 squared. And so what's this? So this is okay. We can express this in the following way. And actually, this is just what? This is, well, we know that we know this relation, yeah? Sum of xi squares equals to x0 squared minus 1, right? We got it from the equation of hyperbolic, yeah? So here we have, sorry, let's change, let's change color. What? What? Actually, don't hear you right now. Sorry. So okay. Let me repeat them. This was gotten from this equation, yeah. This is a defining equation for hyperbolic. Okay. So put your name maybe. Okay. Actually, yeah, and so we can simplify this way, and this is x0 plus 1 divided by x0 minus 1. Yeah, you see this probably in the corner. Okay. So yeah, and what's now? What now? So let's compute dy. So dy is just d of what? Xi over x0 minus 1. Yeah, since we have yi, actually I should compute it before the lecture by myself, not just improvising. So you probably remember that we computed yi's already, and then we take this, and then and then just to compute dyi from dxi is to taking this, so dxi. So this is just like a usual derivation. So divided by 0 minus 1 minus what? Minus xi dx0 x0 minus 1 squared. Yeah? Do you need some explanation for what I did? Okay, so I told you that instead of dyi, you just put something like derivation of your coordinate by time t. So you just take this. So this is just a derivation of this. So you just compute your way for derivation of these functions. So this is a complex function, not complex valued, but just some complicated function. So it is xy divided by x0 minus 1. Those are coordinates, so we can take the x's of them. And just consider this as a derivation by t, for example. Yeah, in your imagination. Then this is a formula for derivation of this fraction, right? Yeah, so UII is related with dx's with this formula, and so what? So we remember that we took, so from here, we remember from here, actually, we remember that our metric tensor look like this, yeah? And then you just substitute. So you need just sum this up, divide by 1 minus squared norm of y, which is also squared, and then multiply by 4. And then you just substitute this expression. Right? So this is 4 multiplied by what? Actually, in the denominator, so we need to express this with coordinate of x. Oh, nothing more simpler, actually, for now, since we already know that norm of y, probably in dots here, norm of y is this. So we have like x0 plus 1, here x0 minus 1, and here we need to substitute sum of, well, this part, yeah? And what is this actually? This is just sum of the squares for these things. And how to do this? Probably I need more space for this. Okay. Let me compute first. So here is, let me put this as sum of dy squared. So let us compute your dy squared. Yeah. So this is dxi squared divided by x0 minus 1 squared plus xi squared dx0 squared divided by x0 minus 1 fourth power, yeah, and minus 2 xi dx0 dxi divided by x0 minus 1 cubed, yeah, okay. And then we need to sum this up. Okay, how to do this? Sum of dy squared, squares of dy is just sum of dxi square, so this divided by x0 minus 1 squared plus what? Plus sum of xi squared multiplied dx0 squared divided by x0 minus 1 fourth power, and minus what? Minus this. So minus sum over I dxi dx0 x0 minus 1 cube, right? And yeah, so just okay, so just so, and what we know already actually, so the sum of xi squared we know actually. I already mentioned this a third time today. This is x0 squared minus 1. And sum of xi's. Sum of xi's is not defined. Well, okay. This is not an expressible thing for now. Okay, actually I already spent my space. Okay, so this is sum of dxi squared divided by x0 minus 1 squared. And here we have 0 squared minus 1 divided by x0 minus 1 fourth power, dx0 squared and minus 2 sums of psi dxy dx0 divided by 0 minus 1 squared. Yeah. So, very interesting actually. Am I correct? Probably yes. Actually somewhat strange, but okay. I thought this would be different. Probably I should recompute it at home. And yeah, since actually, since actually those dxi's are actually dependent to each other. So my future idea will be to express what? Actually, so I have this equation, right? Yeah, of hyperbolic. So I can differentiate it. So yeah. It's very probable that we will cancel out this second term and then express this. Actually, well, okay. Here so this is 0 since we have this equals to constant, yeah, and differentiation of a constant is 0, and differentiation of this is actually minus x0 dx0 plus x1 dx1 plus etc. plus xn dxn, yeah. Sorry, 2 times, since I'm differentiating squares. Yeah, do you follow me? Okay. Please tell me if not. And so, actually, we have that 2x0, sorry, 2x0 dx0, yeah, even without 2, equals 2x1 dx1 plus etc. plus xm dxm. And this is what we here. So this is just x0 dx0. And this is simplifiable. And actually, I thought this would be even more simplifiable, since actually the metric, there should be, well, I hope that I will get the correct answer, but it is proportional to what I would desired, since actually my matrix should be dx0 squared plus dx1 squared plus etc. plus dxn squared. This is just Euclidean metric tensor, which is how to say, ограничить in English, which is restricted to this hyperboloid. So this is just Euclidean metric tensor restricted for this hyperboloid. This should be at least, but it seems that okay, somehow we got somewhat proportional to this. Don't know how this happened. So it is so it will be just divided by x0 minus 1 squared. Okay, maybe I should recompute this at home. Well, the answer is so Alexei computed it already and says that it okay. Probably I will attach some. Probably you can okay, then okay. My bad. Okay, so let us return to our presentation and finish in several minutes. So we have those metrics. Actually, we will meet those metrics tomorrow when we talk about applications. I have very how to say this, interesting talk with you tomorrow. I will try to be as serious as possible tomorrow, actually, but jokes are attending from me outside. Okay, so there is some beautiful mathematics for the elementary part. Let's have a rest. So some elementary definitions. Okay. What is cross ratio? In Russian it is двойное отношение, and this is this fraction of lengths is 4 points A, B, C, and D. This is just a relation for these Euclidean distances. Well, actually there was an exercise which we skipped, that it is preservable by inversions and thus by stereographic projections. So it is good to set this as a function of hyperbolic distance and define this distance from this notion in Poincare, upper half space, and hemisphere models. Why? Because I told you that this was about so their motions are just compositions of inversions and Euclidean motions, right? And this relation is preserved by Euclidean motions, yeah, and by inversions, as I told you. So this is might be a good function from hyperbolic distance, since it doesn't depend on your motion, on any motion, doesn't change. So here are its properties. Actually, the last one is that it differs for if you differ on 1 point. Okay, this was half ratio. And how to define the distance. So in upper half plane model, we take distance as modulus of natural logarithm or just any logarithm for this cross ratio. And this can be for what? So this is a boundary line for our upper half plane here. So we take line connecting A and B and intersect it. So we take ideal points Q and P. So those are intersection with our bordering line. Yeah. So and we take this logarithm of cross ratio for those 4 points. Okay. And there are theorems that it can be computed in terms of angles. So here is angle alpha, here is angle beta for points A and B. And then this is computable by this formula. And for 2 points which lie in the same vertical line in this model, then just take logarithm of their heights of fraction for this y coordinates, for this vertical coordinate. Okay. Actually, there was small talk about section of curvature, which might actually maybe actually about those tensors, and our time is spent actually. So probably tomorrow we will continue with this. Actually, what I would like to mention you tomorrow. Actually, there are hyperbolic analogs for law of cosines and law of sines. So actually, I told you that hyperbolic geometries differ by depending on parameter k. They are similar to each other, and here we see hyperbolic law of cosine. Nearly Pythagoras theorem. So this what I will talk. Yeah, it is the limit for low curvature.
I understand that for large A, curvature limits to 0.
Mm-hmm.
Okay, because you have given the expression for the curvature.
Mm-hmm.
But still, this localness is only in that sense. Right?
Yeah, only in this sense. Yeah. So locally in hyperbolic geometry with small curvature, we won't see. When k is large, we won't see the difference with Euclidean geometry.
Pythagoras theorem in Euclidean case is some geometrical concept, right? It is not just algebraic. It means like how the distances are related.
Yeah.
Here we have some hyperbolic cosines.
Mm-hmm. Actually, there is I didn't put it here. There is a hyperbolic Pythagoras theorem analog. Well, okay. What?
I want to imagine this.
Image.
For cosine.
Okay. I will.
With Pythagoras theorem, we can add the segments
So you want to imagine Pythagoras theorem? Well, I will think about it for tomorrow or probably Monday.
I mean, if it is possible.
Yeah. I will try to think about it. I didn't think about it earlier. So actually, we will have some interpretations for hyperbolic cosines, and for applications. And yeah, we will imagine something at least. Probably not everything. Well, okay. So, any other questions?
Maybe it's not representative because it's more like knowledge and relativistic. They are not just imagined. They just have a parameter.
Okay, actually, we will have very crazy talk tomorrow.
We will not spoil our topic of the time.
Actually, well, I will hold myself from talking about such things as inner part, such as inner universe or something like this. Actually, when I thought through this was what was kind of my mind constantly. Where is that? Well, no. Well, there will be not just esoterical explanation, but also materialistic one. So don't worry. Okay. Okay. So, yeah. Okay. Thank you for your attention, and just put your names in this paper sheet. Okay. So. I stop the translation. So no, I saw. Sorry, I stopped the recording.